Now let's take a look here at example number 4. This will be our first example of a definite integral using a trig substitution. Alright, now not a lot is going to change here. If you think about a u substitution with a definite integral, you might recall that some things are a little bit different than with indefinite integrals. With a u substitution, typically we would also have to change the bounds of our integral when performing the substitution, and we don't really have a requirement to get everything back in terms of the original variable of x near the end, right? I don't have to worry about replacing all of my u's back with x's because I can just evaluate my integral using my new bounds for u. Well, in this case, we're going to have the same sort of setup. Let's start by just thinking about our substitution that we're going to make for x. So I'm just going to start by thinking I need a number that when I square it, it creates 1/4. Well, the number 1/2 jumps to mind for that. And now I have to think a little bit ahead. When that 1/4 is in common between both terms and I factor it out, I'm going to have 1 minus a trig function squared. What trig function would make this an identity? Well, there's two options, a sine or a cosine. I'm going to choose the sine here. So now with this selected, I'll be able to go ahead and say that my dx is 1/2 cosine theta d theta. I'm going to have to do some sort of an angle restriction most likely, so I'll set that up here. I just don't know exactly what. And I'm also going to have to make sure that I understand how my bounds are going to change. Now let's take a look at the bounds and how they change. Keep in mind right now, these bounds, -1/2 and +1/2, are bounds on the variable of x. So typically, when we were doing a u substitution, we plugged in our values for our bounds in place of x. And so we have to do the same thing here. Notice that I'm going to have my -1/2 in place of x is going to produce this, which of course in turn tells me that -1 has to be equal to the sine of theta. Notice I can do the same thing with my other bound of +1/2, and that tells me that 1 is equal to the sine of theta. The question is from here, what does theta have to be to make these values pop out? And here's the dilemma. Aren't there multiple values of theta that can make the sine turn into -1? Some of you may have been thinking, oh, Kyle, sine is -1 when you do 3 pi over 2. And you're absolutely right, but it also works if you do -pi over 2, or if you do a whole bunch of other values. There's infinitely many ways to make these work. And so for the moment, we're going to have to kind of delay our answer here, just like we're delaying our restriction on the bounds. Until I know where theta lives, I can't really evaluate or determine the angles. So let's work through a little bit of what we have, and we'll kind of see we'll have to fill in the blanks as we kind of work through this question. So I have an integral that looks like this. So that should be a 1/4. With our substitution, we know that we're going to have mystery bounds for the moment. I'm going to speed up a little bit of work on the inside and note that if I go ahead and make my substitution, I'm going to be able to have that common 1/4 that factors out, then my 1 minus my sine squared. In place of dx, I know I'm going to have a 1/2 and a cosine of theta d theta. Now simplifying my inside a bit more, I'll see that if I was to square root the 1/4, I get a 1/2. Underneath the radical, I'm going to end up with a cosine squared, and when square rooted, that creates absolute value of a cosine. And so I'm left with this. Now fortunately, my 1/2, 1/2, and my 4 all cancel out. But it's again at exactly this step where it's very important to understand my angle restriction. So I need to pick a range of angles where theta is always positive. Well, that could, or sorry, where the cosine of theta is always positive. So that would definitely be on a range of angles like -pi/2 to +pi/2. Right? This is definitely a range of angles where the cosine is always going to be positive. It's quadrant 1 and quadrant 3. Or sorry, quadrant 4. So now I can go back and update my bounds. take a look at this upper bound that I have. Where would the sine of theta equal 1 if theta has to be one of these angles? Well, it would have to be at pi over 2. So I can go back and kind of fill in this upper bound of pi over 2. But if the sine is supposed to be negative 1, and theta's got to be one of the values in here, what value can I choose? Notice I can't choose 3 pi over 2. That's not an option. So I'm going to be left choosing negative pi over 2. And that would then be my lower bound. So if I simplify all of this down, let me just shift this down a little bit further, I'll see that I'm going to be left with an integral that goes from negative pi over 2 to positive pi over 2. And I'd really be able to say that I have cosine squared of theta d theta. Of course, I know that whenever I see like a sine squared or a cosine squared in an integral, we saw that in the last section I'm really going to be interested in trying to replace that with one of my double angle formulas. So in this case, 1/2 times the quantity, 1 plus cosine of 2 theta. Now integrating from here isn't too difficult. I can see that I would just have to go ahead and state my antiderivative as theta plus, and I think I could get away with 1/2 sine of 2 theta. You could double check me by taking a derivative. Then notice I don't even have to worry about switching back because I can just evaluate at the bounds. So notice I'm going to have 1/2 times pi over 2 plus 1/2. Notice here I'm going to have sine of pi, and then minus 1/2 negative pi over 2 plus 1/2, and this is going to be sine of negative pi. Now fortunately for us, the sine of pi and negative pi is just 0. So really I'm going to have pi over 4 for my first item here, my first term, minus a negative pi over 4. So that's going to just turn into a final result of pi over 2. So hopefully this gives you a sense of how, I can complete one of these definite integrals. And I can see that there's some things that are maybe a little bit nicer than the indefinite case. Notice I didn't have to revisit my substitution. I didn't have to solve for theta. I didn't have to draw any weird triangles. The extra work here came in swapping over the bounds. And as long as I can still do that successfully, I should be able to complete one of these types of questions.